It is on the subject of polymorphic type inference for dynamic languages.
Thank you for the introduction. So this is a joint work with Giuseppe Castagna and Mickaël. So let's start with some motivation. I have written here a function in JavaScript. It simulates the behavior of the logical OR. So it takes two parameters, x and y. First, it converts x to a Boolean. If it results in the value true, then it returns x. Otherwise, it returns y. What we want is to type this function. But first, let's focus on toBoolean. So toBoolean is a function that takes a parameter. If it receives the value false, null, 0, the empty string, or some other values, it returns false. And for any other value, it returns true. What we're going to do is to give a name to the set of values that converts to false. We're going to call them falsy. And the other values, we are going to call them truthy. And now we can give a type to toBoolean. We can type it with the following type: falsy to the singleton type false, and truthy to the singleton type true. So here we have an intersection in the type, and it is used to capture the overloaded behavior of toBoolean. The first branch, falsy to false, describes its behavior when we give it a falsy value, and the second branch, truthy to true, when we give it a truthy value. So now we can try to type the logical OR function. The type we want to give it is the following one. So this type is both polymorphic and overloaded. The first branch describes the behavior of logical OR when the first parameter is a truthy value. And in this case, this type says that it returns exactly the first parameter. And the second branch corresponds to the case where the first argument is falsy, and in this case, it returns the second argument. If we want to be able to derive such a type, we have to overcome some challenges. First, we have to perform type narrowing. Indeed, when we type the first branch of the type case, the return x, we should assume that x is truthy. It is the case because if x was not truthy, then it would have taken the second branch. In order to implement that, we will use union types. We will see that later. Also, we want to capture overloaded behaviors. And as we have seen, we do that using intersection types. And also, we want to capture genericity in order to be modular. And for that, we use parametric polymorphism. Okay. So now let's define our types and language. We will use what we call set-theoretic types. So set-theoretic types provide the usual construct. So we have the base type, the singleton type, the integer, etc. Then we have the type variables. We have the arrow for function and the product for pairs. But they also provide a way to express the union of two types, the intersection of two types, and the negation of a type. Also, we have the special type empty that has no inhabitant, and its negation any that is the type of all values. We can define the subtyping relation on these types. It has been done in prior work, so we will just assume that we have such a subtyping relation. Now for our language, we will use the usual call by value lambda calculus with an additional construct for type cases. The semantics of type cases is as follows. First, we reduce the test expression. If it results in a value that has type t, then it reduces to the first branch, and otherwise to the second branch. So now let's build the type system. We start with some usual rules. So we have a rule for constant, for variable, for lambda abstraction, and for application. Also, as we have subtyping, we have a subsumption rule. Now we are going to add some more rules in order to increase the expressivity. So these rules are from the natural deduction logics. The two first are used to implement prenex polymorphism and come from Hindley-Milner systems. The third one comes from intersection type system, and the last one from union type systems. So none of these rules are new. They all exist from prior work, but our work consists in combining them into a single type system. So let's see that in more detail. For polymorphism, we have two rules. A gen rule that allows to generalize type variables of top-level definitions. And then we can instantiate them with an instantiate rule in a later definition. Then we have the intersection introduction, which states that we can derive the type T1 and T2 for the expression E, if we can derive the type T1 for E and the type T2. And lastly, we have the union elimination rule. Given an expression E, this rule allows to select any subexpression E prime and to decompose its type into a union, S1 or S2, and then we can treat each case separately. So first we type E by assuming that this subexpression has type S1, and then we type E again, but this time by assuming that this subexpression has a type S2. This union elimination rule allows to perform type narrowing and to type cases. The idea is as follows. We combine this rule with two simple rules for type cases. The first one corresponds to this special case where the test is always true, and thus we only need to derive the first branch, to type the first branch. And the second one is the opposite case, when the test is always false. In this case, we only need to type the second branch. Of course, these two simple rules alone do not capture the general case, but in combination with the union elimination rule, it does. We can see that with an example. Here we have a simple function. It takes a parameter x. It tests whether x is an integer. If it is the case, it returns x plus 1. Otherwise, it returns false. So we want to type it for the domain any. So we enter in the lambda with the rule for lambda abstraction, and we assume that x has type any. But no, we cannot type the type case directly because we are not in this special case. So instead, we apply the union elimination rule in order to study separately the case where x is an integer and the case where it is not an integer. And so for the case where it is an integer, now we can type the type case using the first type case rule. And note that the first branch is typed under the assumption that x is an integer. And then we can treat the second case where x is not an integer, and this time we type it using the second rule for type case. And in the end, we are able to derive the type any to int or false for this function. But actually, there is another way to derive the type for this function, this time by using the intersection rule. So we are going to type it again, but this time we just want to type it for the domain int. So we enter the lambda and assume that x is an integer, and we can directly conclude with the first type case rule. And it yields the first type of this lambda expression, the type int to int. And now, independently, we are going to type it for the domain not int. And here, again, we can conclude directly with the second type case rule, and it yields the type not int to false. And as we have two types for the same lambda abstraction, we can combine them by applying the intersection rule. So, as we have seen, there are several possible derivations which may yield different types. And this is an issue because we want an algorithm. Actually, there are several sources of non-determinism. First, some rules can be applied on every expression, making the system not syntax-directed. This is the case of the union elimination rule, the intersection introduction, the instantiation, and the subsumption. Also, in some rules, some premises cannot be guessed from the conclusion. This is the case, for instance, in the union elimination rule of the type decomposition, or it is the case when we have a lambda abstraction, we have to guess the type of the parameter, or in the instantiation rule, we have to guess a substitution. So now the challenge is to make the type system algorithmic. In order to do that, we have to choose a strategy. What we choose to do is to apply the union elimination rule once on every distinct subexpression. And by doing that, we do not lose any generality. In order to help us to implement this behavior, we are going to transform the expression we want to type into what we call the maximal Turing canonical form. It is a form which gives a unique name to each distinct subexpression. So for instance, for the pair f of x, we first define f of x and bind it to the variable u. And then we define the pair u and bind it to the variable v. The advantage of this form is that now we can just apply the union elimination rule once on every bind expression. Okay, but still we have to guess a type decomposition out of nowhere. And for lambda abstraction, we also have to guess the type of the parameter, etc. So in order to solve this issue, our algorithmic type system is going to take an additional input So in addition to the maximal Schrödinger canonical form, it is going to take an annotation tree, and both together, these two elements will uniquely encode a derivation. So here, for instance, we have on the left the maximal Schrödinger canonical form, consisting in a binding, and on the right, we have an annotation tree, which says which type decomposition to perform. And so it yields the derivation below. But now we have only moved the issue because now we have to infer these annotation trees. Okay, so I'm just going to cover the main ideas. So we have to infer the type decomposition to apply when we apply the union elimination rule. And for that, we will look at type cases. When we encounter the type case z in true, then x else y, what we're going to do is to backtrack to the definition of z and to split its type into true and not true. Okay. And also, we have to infer the type of parameters. And for that, we will use what we call tallying. And basically, it is like unification, but with subtyping constraints. So for two types T1 and T2, we want to find all substitution sigma, such that T1 sigma is a subtype of T2 sigma. It is decidable. We can compute the solution, and the solutions are characterized by a finite set of substitution. So let's see that with an example. It is the example from the introduction, and we want to infer the types of the parameter. So first, we start by typing x with alpha and y with beta. And then we want to type two Boolean of x. So for that, we generate a tallying instance that encodes the fact that this application is well-typed. And then we solve this tallying instance. And in this case, the solutions are characterized by two substitutions. The first one that suggests that alpha should be substituted by alpha prime and true phi. And the second one that suggests that alpha should be substituted by alpha prime and false. And so now what we do is we backtrack to the definition of x, and we treat each case separately. So first, we type the body again, but this time by assuming that x has the type alpha prime and true phi. And in this case, we can type it and it yields the type alpha prime and true phi. And then we type the body again by assuming that x has the type alpha prime and false. And in this case, it yields the type beta. And so we have two types for this function. We just take the intersection, and we have inferred the type from the introduction. So in conclusion, we have defined a declarative type system that mixes union type, intersection types, and polymorphism. And we have proved some type safety theorem for it. Then we define an algorithmic type system that is sound and complete, but that require annotations. And so then the last part is to infer this annotation. And for that, we use tallying and backtracking. So our inference algorithm is not complete, but it is terminating. But as it is not complete, sometimes we might need some user type annotation to help it. It has been fully implemented in OCaml, and you can test it online. No need to install anything. And to finish, I want to highlight some ongoing work. We are working on supported side effects because in this work, we assume that our language is pure, because if the language is not pure, the use of union elimination must be restricted in order to be sound. Also, we want to add how polymorphism for records, to type records, because records can be used to encode objects, so it is useful, and we want to type them precisely. And lastly, we are working on applying it to real-world languages, such as Elixir or Python. Thank you for your attention.
Thanks, Mickaël. So we have plenty of time for questions.
Thanks for the talk. I have two small questions. The first one is about complexity in general. It seems that even just checking subtyping should be maybe exponential.
It is. So yes, we have no theoretical guarantee for complexity. So yes, even just the subtyping is exponential. So in practice, we don't want types that are very complex. We don't want types that has many overloaded intersection. I think it's not readable for the user. And so the challenge, we have to find the sweet spot to keep type as simple as possible, but still sometimes we will need some intersection, but there is a sweet spot to find in order to have good performances.
Thanks. Are you using SAT or solvers or specialized procedure, or just something that in your actual implementation to decide?
We do not rely on any external solver. Actually, we use, in my prototype, use an implementation of set theoretic types that has algorithm to decide subtyping. So I just use this library to decide subtyping, and otherwise there is no dependency.
And secondly, do you know if your type system has the property that every expression always has the smallest type? Is your lattice of types complete in a sense?
We do not have type principality. So for some expression, yes. For instance, if you want to type the map function, you can say that just it takes a function from alpha to beta and then a list of any number of alpha, and it returns a list of any number of beta. But you can also say that if you give it as second argument the empty list, then it returns the empty list. And you can also say that if you give it a singleton list as first argument, it returns the singleton list as second argument, etc. And you can do infinitely many intersections. Each time you have a more precise type. But so we don't have type principality because we would need infinite intersection.
Makes sense. Thanks.
So I wanted to ask you again, maybe a related question about the performance of the intersection and union types, because your type inference algorithm has a lot of backtracking in it. So when you've used it, have you found that like it's very sensitive to the order you write the unions in, or things like that?
It is not sensitive to. So the types used are not syntactically defined. It is set theoretic types. So the subtyping is semantic subtyping. So the order of things, it might impact the performance, but I do not really have the very much control on it. We always reason modulo semantic equivalence. So then it's the set theoretic types library that should try to optimize it as it can. And yeah, for the performances more generally, it works well as soon as it can really take a lot of time to infer sometimes if we have, for instance, recursive function with a lot of first order parameters. In this case, the inference tries to do too many branches. It is, and so it will not terminate in a reasonable type. But then the user can help it and add type annotation. And in this case, it cuts a lot of branching and backtracking. And in the end, if the user annotates every parameter, the performance are good.
Okay, thank you.
So if there's one more quick question, we could take it.
So in Erlang or in Elixir, there's this notion of a hot code swap where you compile some program at runtime and switch a module. Right? Is there a way of typing such a thing? Let's say, okay, I'm going to compile the program, it has type any, and I mean, at the moment there's this tool called Dialyzer that will sort of success type an Elixir program. But
I'm not sure to understand. Can you reformulate, please?
Yeah. So I receive a term right from. I wrote a distributed program. I received from a different machine a term. Right. I cannot know the type of this term, and sort of Elixir programs can compile other Elixir programs at runtime. So then, can I give this new program type any?
Yes, you can type. You can type any program. I mean, there is the typing of values. There is two different things: the typing of values and the typing of expression. So for determining when we have type cases, and we test whether a value has the type of the type case or not. It uses a very simple typing. We just basically type any lambda abstraction with empty to any. And so for runtime checks, it's a very basic type system where everything can be typed with any. But if you for expression as statically, we cannot type anything with any because a lambda abstraction must be well typed in order to be typable. But we can add graduate typing. This has been done. I have not integrated it in my prototype, but you can add graduate typing with a joker type that allows to type anything with this joker type and then or dynamic type. It depends on how we call it. Okay.
Thank you.
Okay, let's thank Mickaël again. And that concludes the session.